In an infinite universe filled with billions of galaxies and stars, there exists a small blue planet where matter has not only become alive but conscious, capable of asking questions, seeking meaning, and reflecting on its place in the cosmos. The lecture you are about to read is a remarkable and thought-provoking exploration delivered by Professor Brian Cox, a renowned theoretical physicist and public educator. In it, he examines, through both scientific rigor and philosophical depth, what it means to exist, to observe, and perhaps even to matter in this vast and ancient universe. This talk was delivered in April 2025 in San Diego, California, where I had the privilege of attending the conference in person. I have done my best to carefully document and reconstruct the core ideas, scientific concepts, and philosophical insights presented by Professor Cox so that you may also benefit from the wisdom he shared. Throughout this lecture, Professor Cox takes us on a journey that stretches from the event horizon of black holes to the earliest moments after the Big Bang, from the paradoxes of time and information to the possible origins of life in distant worlds, and perhaps even here in our ancient oceans. Drawing on general relativity, quantum mechanics, and modern cosmology, he guides us through some of the deepest questions facing science today. But more than a scientific summary, this lecture is an invitation to wonder, to responsibility, and to meaning. If consciousness is rare in the universe, then perhaps we ourselves are its meaning makers. Perhaps through our curiosity, our survival, and our pursuit of understanding, we breathe significance into a universe otherwise indifferent. The following 10 sections represent a detailed account of this extraordinary lecture. Each one is a chapter in an ongoing human dialogue with the cosmos. I invite you now to join in that dialogue with open eyes, an open mind, and a deep sense of shared purpose. Section 1. A fragile life in an infinite universe. Cosmology is arguably one of the most intellectual and challenging of the sciences. It's not just science, it also confronts us with deep philosophical questions. What does it mean to live a finite, fragile life in an infinite, eternal universe? Professor Brian Cox. With this stirring invocation, Professor Brian Cox invites his audience on a journey not just through the stars, but through the deepest recesses of human curiosity. Cosmology, he suggests, is where empirical data collides with existential wonder. It is not merely about galaxies and black holes. It is about us, our place, and the meanings we construct as fleeting beings in a cosmic sea billions of years in the making. To set the stage, Professor Cox presents a breathtaking photograph, a stitched image of the entire sweep of the Milky Way galaxy, as seen from both the northern and southern hemispheres of Earth. This is not a view we can ever witness in real life from a single vantage point. It is a synthetic miracle of astrophotography, mapping out the band of light that is our galactic home. He points out notable features, among them the galactic center, a region we cannot see directly from Earth, buried beneath dense clouds of interstellar dust. Yet nestled within it lies a supermassive black hole, a gravitational giant we'll revisit later. Off to the side, we find the Magellanic Clouds, small satellite galaxies orbiting the Milky Way. Vivid little cities of stars, as Cox poetically describes. From there, our gaze shifts outward. The Andromeda Galaxy, the nearest large galaxy to our own, is visible to the naked eye in dark skies. It is 2.5 million light-years away, meaning the light we see tonight left that galaxy before humans had even evolved on Earth. When you see Andromeda, he says, you're seeing light that began its journey before there were eyes on Earth to witness it. This is the staggering scale of the cosmos. Each point of light a time capsule, each galaxy a sprawling metropolis of suns and planets. The Milky Way alone hosts around 400 billion stars, and thanks to modern exoplanet surveys, we now estimate that at least 1 in 5 of those stars likely harbors an Earth-like planet, potentially 20 billion rocky worlds within our galaxy alone. Professor Cox remarks that every star you see in the night sky is likely to have a solar system of its own. The number of potentially habitable planets begins to exceed comprehension, and we are still only speaking of our galaxy. Next, he introduces a stunning image of the Whirlpool Galaxy, M51, located 23 million light-years away. What makes it more awe-inspiring is that it's colliding with a dwarf galaxy, a galactic merger frozen in time. These immense systems, spanning tens of thousands of light-years, interact gravitationally over epochs, flinging stars into new orbits and birthing fresh waves of star formation. And then comes a humbling truth. The Andromeda Galaxy, that visible neighbor in our skies, is on a collision course with the Milky Way. In about 5 billion years, the two galaxies will merge, creating a new galactic structure. Though the stars themselves are unlikely to collide due to the vast distances between them, the event will radically reshape the cosmic architecture we know. Such collisions are not rare. The James Webb Space Telescope, JWST, launched to peer into the deepest reaches of the universe, sends back images of galaxy clusters billions of light-years away, filled with cosmic collisions, gravitational lensing, and fossil light from the early universe. In one of its first iconic images, JWST revealed Stephan's Quintet, a compact group of galaxies engaged in a cosmic dance. But beyond the central cluster lies something even more profound. Background galaxies, dim red smudges that are in fact light from the early universe, distorted and magnified by gravity. When we look far out into the universe, we look back in time, Cox reminds us. Some of that light began its journey over 13 billion years ago. This is what cosmology offers, the ability to witness the past not just in theory, but through photons caught in our telescopes, evidence of creation itself. As we venture further, Cox introduces the Sloan Digital Sky Survey, a 3D map of real galaxies in space. When animated, the map reveals the cosmic web, galaxies forming filaments and clusters with vast voids in between, a structure that echoes the early density ripples of the universe itself. It looks like a snowstorm, he says, but it's not random. It's a pattern, a fossil of the forces that shaped the cosmos before galaxies and stars even existed. We now estimate that the observable universe contains around 2 trillion galaxies. That number alone is overwhelming, but it also points toward the grand ambition of cosmology, to understand the origin and evolution of everything. From the quantum fluctuations of the vacuum to the birth of stars, from the collisions of galaxies to the emergence of consciousness, this is the domain of cosmology. And here lies the philosophical thrust of Professor Cox's message, that science, and especially cosmology, forces us to confront the vastness of space, the brevity of our existence, and the delicate improbability of meaning in a cold, indifferent cosmos. Science doesn't strip meaning from the universe, he argues. It gives us the tools to recognize that meaning is rare, fragile, and perhaps miraculously ours to protect. With this powerful beginning, Professor Cox draws his audience into a universe that is not only vast, but alive with mystery, motion, and mathematical elegance. Section 2. The collapse of stars and the geometry of space-time. There will always be some kind of physical process that will resist the gravitational collapse of a star, many physicists once believed. That belief was driven not only by the strangeness of the predictions, but also by a resistance to accepting something that felt absurd. As Professor Brian Cox recounts, British physicist Arthur Eddington famously said in the 1920s, "Nature will prevent such absurdities from happening." But nature, it seems, is not bound by our sense of the absurd. We now know that if a star is sufficiently massive, about 3 times the mass of our Sun or more, then no known force halts its final collapse. When such a star exhausts its nuclear fuel, the inward pull of gravity wins. It collapses into an incredibly dense point, what we call a black hole. Importantly, in Einstein's theory, the collapsing star doesn't simply disappear. Rather, it leaves behind a permanent imprint, a distortion in the fabric of space and time. The geometry is still there, Cox says, even if the star is not. To understand this, imagine a clock hovering above the collapsing star. Previously, the clock couldn't fall inward because the star's surface blocked it. But once the star has collapsed, the clock is free to descend further into the warped space-time left behind. Einstein's equations predict something astonishing. There exists a place in space where time stops, the event horizon. Cox highlights the absurdity physicists grappled with. What does it mean for time to stop? Is that a boundary? A limit? Worse still, inside this horizon, time behaves strangely. According to the equations, it appears to reverse. The first physicists to calculate that stars might behave this way were Robert Oppenheimer and his student Hartland Snyder, who in 1939 showed that massive stars would indeed collapse into such objects if Einstein's equations were correct. Their result was so uncomfortable that many dismissed it. To explore what these equations imply, Professor Cox introduces a map, a Penrose diagram, named after Sir Roger Penrose, who developed it in the 1960s to visualize space-time, especially in extreme conditions like near black holes. Penrose diagrams compress infinite distances and times into finite space on a page, allowing us to see the entire history of the universe, past, present, and future, in a single image. Cox first shows a simple diamond-shaped diagram representing an eternal, infinite universe, and then distorts it to represent a universe with a black hole. Inside the black hole, a singularity forms, not just a point in space, but a moment in time where time itself ends. Cox sends an imaginary astronaut into the black hole. She crosses the horizon and continues ticking 1 second per second, but the singularity lies in her future, and she cannot avoid it. This inversion of roles, where space becomes time and vice versa, is perhaps the most mysterious feature of general relativity. The singularity is not a place you can navigate to or around. It is an inevitable moment in the astronaut's timeline. To make this concept tangible, Cox presents an Einsteinian simulation of a black hole developed using general relativity equations. As the camera orbits the black hole, the accretion disk, the swirling matter around it, is distorted. Light curves around, forming arcs and duplicate images of stars, a result of gravitational lensing. He shows the audience how this simulation predicts what a real black hole would look like, and then reveals the actual image taken in 2019 by the Event Horizon Telescope of the supermassive black hole in galaxy M87. It looks nearly identical to the simulation. The segment ends with an inspiring reflection. By studying these objects in the sky, we are not just learning about extreme physics. We are confronting the fundamental nature of space and time, and the ultimate fate of information, matter, and perhaps ourselves. As the lecture unfolds, Professor Brian Cox takes us deeper into the structural architecture of the universe, guiding us from images of individual galaxies to the vast and intricate latticework of matter known as the cosmic web. This, he states, while presenting a breathtaking visual dataset, is now a visualization of real data. This data was sourced from the Sloan Digital Sky Survey, a major astronomical project that mapped the three-dimensional positions of galaxies in the observable universe. The animation we see on screen is not a simulation. It's a fly-through of genuine astronomical observations. Each point of light represents a galaxy. Each galaxy potentially contains hundreds of billions of stars. What initially appears as a chaotic scatter, like a snowstorm, soon reveals patterns, vast voids where no galaxies exist, and flowing filaments connecting dense clusters of galaxies. These patterns are not random. They form what scientists call the cosmic web. This network is the large-scale structure of the universe. It's almost like an etching. The universe isn't just a random scattering of galaxies. It's a tapestry woven by physical laws, revealing the echo of something that happened long before stars and galaxies existed. From this web, cosmologists derive their core inquiries. Why are galaxies distributed in this way? What primordial events etched this pattern into the structure of the universe? How many galaxies are there in the observable cosmos? Professor Cox notes the current estimate, 2 trillion galaxies within the observable universe. This vast number not only boggles the mind, but challenges us to refine our understanding of cosmic evolution and the laws that govern it. He explains that the cosmic web wasn't born with galaxies. It predates them. These patterns emerged from minute fluctuations in the density of matter in the early universe. Gravity amplified these differences over billions of years, forming galaxies and clusters in the denser regions, while less dense areas became cosmic voids. This raises a profound question. What seeded these primordial fluctuations? Cox hints that later in the lecture, we will discuss the theory of cosmic inflation, a concept that aims to explain not just how the universe expanded, but why these fluctuations existed in the first place. The aim of cosmology, Cox emphasizes, is not merely to observe the universe, but to understand it, to reveal the story encoded in its structure, to interpret the cosmic patterns like archaeologists deciphering ancient scripts. To conclude this section, he presents a striking full-sky image captured by the James Webb Space Telescope, JWST. This image, referred to as the Goods North Field, showcases thousands of galaxies, each a unique island of stars. Some galaxies in this photograph are so distant that their light has traveled for over 13 billion years to reach us. We are seeing them as they were shortly after the birth of the universe. This image is not only a time machine, it's a testament to the sheer scale and depth of our cosmos, and it serves as a foundation for the next exploration in the lecture: Einstein's theory of general relativity and how it revolutionized our understanding of gravity, space, and time. In the words of Professor Cox, these photographs are more than beautiful, they are revelations. They're the imprints of the universe thinking itself into existence. One of the most profound insights from modern cosmology, as highlighted by Professor Brian Cox, is the realization that the universe is not static, it is expanding. This discovery, rooted in both theory and observation, dramatically altered our understanding of the cosmos. As Professor Cox describes, when we apply Einstein's general relativity not just locally to stars or black holes, but to the entire universe, the result is startling. The fabric of the universe itself must either expand or contract. It cannot remain static. Einstein himself initially resisted this implication. Favoring a stable, eternal universe, he introduced the so-called cosmological constant into his equations to balance out the dynamic behavior predicted by general relativity. However, subsequent observations, particularly those by Edwin Hubble, showed that distant galaxies are moving away from us, confirming that the universe is indeed expanding. This expansion implies a past that was once denser and hotter, a concept that led to the formulation of the Big Bang theory. As Cox puts it, if galaxies are flying apart today, they must have been closer together in the past. Trace this logic back far enough, and you arrive at a moment when all matter and energy are concentrated in a single, unimaginably hot and dense point, the origin of our universe. Supporting this theory is one of the most iconic images in modern science, the cosmic microwave background, CMB. This radiation is a relic from the early universe, emitted about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form, allowing light to travel freely. Cox explains, "This photograph of the universe is different from what we see today. There are no stars or galaxies yet, just hydrogen, helium, and minute temperature fluctuations, tiny ripples left over from the earliest moments. These ripples, measured by satellites like COBE, WMAP, and Planck, are not just noise. They represent slight variations in density that eventually collapsed under gravity to form stars, galaxies, and everything we see today." To illustrate the precision of this data, Cox quotes physicist George Smoot, who led the COBE team. "These images are like looking at the face of God." The reason is simple. These fluctuations are the seeds of all cosmic structure. Without them, the universe would be a smooth soup of particles, devoid of galaxies, stars, or life. Further validating the Big Bang theory is the prediction and eventual discovery of this cosmic background radiation. Intriguingly, it was discovered by accident in the 1960s by Arno Penzias and Robert Wilson, who were trying to eliminate noise from their radio antenna. What they found instead was a persistent signal coming from all directions, a whisper from the infancy of the cosmos. This profound insight transforms the Big Bang from speculative hypothesis to established scientific theory, supported by detailed empirical evidence. And yet, the CMB image is not just a scientific milestone, it is a cosmic mirror reflecting the very birth of time and structure. Professor Cox reflects, "We are looking at a universe that has not always existed in its current form. We are not seeing stars and galaxies, but rather the very conditions that allowed them to form. This is a photograph of the birth of structure itself." Thus, the expanding universe, grounded in Einstein's elegant equations and confirmed by precise measurements, offers not just a scientific narrative, but a philosophical one. It invites us to reflect on beginnings, on emergence from simplicity, and on our place within a universe that once shimmered with the faint glow of creation. As our understanding of black holes deepens, modern theoretical physics has begun to hint at a revolutionary picture of the universe, one where space and time themselves may not be fundamental, but emergent. Professor Cox explains that near the singularity of a black hole, extreme tidal forces, what physicists whimsically call spaghettification, stretch matter into infinitesimal threads. You get stretched infinitely thin in one direction and squashed into zero in the other, he says. Even atoms and subatomic particles, protons, neutrons, quarks, would be torn apart. Some scientists envision the structure of a black hole as a network of wormholes, not quite like science fiction, but perhaps even stranger, through which scrambled information can be transmitted back into the universe. Whatever the mechanism, he adds, what matters is that the outside observer sees something consistent. Information comes out. This gives rise to a profound idea. Space and time might not be fundamental ingredients of the universe, but emergent from some deeper layer of physical law. They may be constructed from quantum bits of information, encoded in the same way quantum computers store and protect information. Cox draws a comparison to human beings. We're made of simple atoms, carbon, oxygen, iron, the same building blocks of planets and stars, but arranged in a particular way, something emerges. Consciousness, complexity, thought. The implication is staggering. Just as consciousness emerges from atoms, space and time themselves may emerge from quantum informational patterns. He references physicist John Wheeler's famous phrase, "it from bit," the notion that reality arises from information. Space-time may be a higher-order manifestation of something more fundamental, invisible, yet mathematically describable. Cox describes how black holes helped expose these ideas. The temperature of a black hole, first calculated by Stephen Hawking in 1974, shows that it emits radiation, now known as Hawking radiation. The fact that black holes radiate implies they have entropy, and entropy in modern physics is understood as a measure of information content. Jacob Bekenstein showed that a black hole's entropy is proportional not to its volume, but to the surface area of its event horizon in Planck units. This leads to one of the most mysterious discoveries in theoretical physics. A black hole behaves as if all the information it contains is encoded on its boundary, like a cosmic hologram. Imagine a library. Intuitively, the amount of information it contains should depend on its volume, how many books can fit inside. But in black hole physics, the number of bits is determined by the area of the walls. This isn't just abstract theory. These concepts underlie one of the most cutting-edge areas of research today, the intersection of gravity, quantum information, and computer science. Professor Cox notes, "It almost feels like the universe is behaving like a quantum computer." It's a poetic image of the universe, not as a lifeless void, but as a dynamic tapestry woven from logic, mathematics, and information. And it all began, he reminds us, from the question, what happens to a clock as it falls into a black hole? That simple curiosity, pursued with scientific rigor, may have uncovered one of the deepest truths about reality, that everything we know, including space and time, may be just the surface of something more profound. Section 6. Time, gravity, and the final frontier within black holes. As our journey into the depths of the cosmos continues, Professor Brian Cox takes us to the edge of one of the most mysterious and extreme phenomena in the universe, the black hole, and more specifically, the nature of time and space within its event horizon. He begins with a striking statement. The prediction of Einstein's equations is that there is a place in space where time stops. This isn't just a theoretical curiosity, it's a profound statement about the very structure of reality. When a massive star collapses under its own gravity, it can form a region of space where, according to general relativity, time comes to an end. To help us visualize this strange and counterintuitive behavior, Cox introduces us to a conceptual tool called the Penrose diagram, a map of space-time where infinity is compressed into a finite region. This allows us to represent an entire eternal universe, and even the formation of a black hole, on a single flat page. Within this diagram, the event horizon, the boundary beyond which nothing, not even light, can escape, is a crucial dividing line between the outside universe and the mysterious interior. The event horizon is not a place where matter disappears. Rather, it is a boundary in space-time. Beyond it, for any observer crossing over, the future inevitably ends at a singularity. If we watched a friend fall into a black hole from the outside, we would see their movement slow down, ever slower, until, frozen in time, they appeared to stop right at the horizon. But from their own perspective, time continues as usual. Their watch ticks normally. Nothing unusual happens as they fall through that boundary. This difference between the perspectives of the external observer and the falling astronaut is a triumph of Einstein's theory of general relativity. Time is personal, not absolute. Cox emphasizes, your time is your own. That's why time can appear to stop for some and continue for others. Once across the event horizon, the astronaut is pulled inevitably toward the singularity, a place where the curvature of space and time becomes infinite. And this singularity is not a point in space, but a moment in time, the end of time itself. Just as you cannot escape the arrival of tomorrow, you cannot escape the singularity once you've crossed into a black hole. He uses the metaphor of a torch beam. If you shine a flashlight outward from inside the horizon, the beam no longer escapes to the universe. Instead, it travels inward, toward the singularity. Cox then dives deeper. Inside the black hole, space and time switch roles. What was once the direction you could move through in space now becomes your direction in time. This means that traveling deeper into the black hole isn't just optional, it becomes as inevitable as moving forward in time. This reversal lies at the heart of the idea that the singularity is the end of time. And as the traveler approaches this final moment, they undergo what physicists call spaghettification. Tidal forces stretch the astronaut vertically and compress them horizontally until even fundamental particles like quarks and protons are ripped apart. The physics becomes violent, overwhelming, and eventually all structure is destroyed. But what happens to the information? That's the deeper mystery, and it's a question that general relativity alone cannot answer. The singularity suggests information is lost, but quantum theory insists it cannot be. This sets the stage for what comes next, a scientific and philosophical battle between the two greatest theories of modern physics, general relativity and quantum mechanics, and the beginning of a search for a deeper understanding of space, time, and reality itself. Section 7. Hawking radiation and the chaos of information in black holes. One of the most significant scientific developments of the 20th century came in 1974 when Stephen Hawking proposed an extraordinary idea that black holes are not entirely black. They emit radiation. This insight, known today as Hawking radiation, challenged classical views about black holes as one-way cosmic prisons. Professor Brian Cox, during his lecture, guides the audience into the philosophical and physical depths of this idea. He refers to the black hole not merely as a collapsed star, but as a region where space and time themselves are so distorted that they alter our most fundamental assumptions about reality. Hawking's calculation showed that a black hole has a temperature. It emits particles near its event horizon, where quantum fluctuations allow for pairs of particles to form briefly, one of which falls in, and the other escapes as radiation. The astonishing implication is that black holes can slowly evaporate. As Professor Cox notes, this revelation leads to what is known as the black hole information paradox. In classical physics, information cannot be destroyed. Even if you burn a book, theoretically, the information it contained is preserved in the smoke, light, and ash. However, Hawking's radiation seems to carry no imprint of the matter that fell into the black hole. When the black hole finally evaporates, all the information appears lost. This violates the fundamental principles of quantum mechanics, which declare that information must be conserved. To address this paradox, physicists have explored multiple hypotheses. Some suggest that the information is stored in the event horizon itself, encoded in minuscule Planck scale bits. This leads to the remarkable conclusion that a black hole's entropy, the measure of its internal information content, is proportional not to its volume, but to the surface area of its event horizon. This idea profoundly shifts our understanding of space. It is as if the three-dimensional interior of a black hole is merely an illusion, a projection of two-dimensional data encoded on its surface. This concept is at the heart of the holographic principle, a modern view suggesting that our universe itself may behave like a vast quantum computer or hologram. Professor Cox continues, "We're beginning to glimpse that space and time are not fundamental entities. They emerge from something deeper, a pre-geometric quantum reality. Just like consciousness or life emerge from configurations of atoms, it may be that the fabric of space-time itself emerges from the interplay of quantum information." He recounts how Hawking's insight led to decades of further research. culminating in efforts to reconcile general relativity with quantum mechanics. In 2019, new calculations suggested that perhaps the information is not lost after all. It is somehow encoded in the correlations between emitted particles and the structure of space-time near the event horizon. Still, the paradox is not fully resolved. Some proposed resolutions, like firewalls, imply that the event horizon is a searing boundary, destroying any matter or information that crosses it. But this would violate Einstein's equivalence principle, which states that an observer falling freely into a black hole should not feel anything unusual at the event horizon. Thus, the mystery deepens. The deeper implication of all this is that our classical notion of reality, of a smooth, continuous space-time, might be an approximation. The true nature of the universe could be granular, digital, fundamentally informational. As Professor Cox summarizes, we may be discovering not only how the universe works, but what it really is. Part 8, the information paradox and the fabric of reality. In this section, Professor Brian Cox delves into one of the most mysterious and intellectually provocative phenomena in physics, the black hole information paradox. He opens with a startling description of what happens as one approaches a black hole. As we get closer to the singularity, those tidal forces become extreme, and what's called spaghettification occurs. You get stretched infinitely in one direction and compressed in the other. This description isn't just theatrical. It captures the very real extreme physics that any object, human or otherwise, would experience near a black hole's event horizon. The speaker notes that even subatomic particles such as protons and quarks would be torn apart in this violent gravitational environment. But it is what happens to information that enters a black hole that lies at the heart of this philosophical and scientific conundrum. Traditionally, black holes were considered one-way destinations. What falls in never escapes. However, Stephen Hawking's groundbreaking work in 1974 suggested otherwise. He discovered that black holes emit what is now known as Hawking radiation, a quantum effect that implies black holes are not entirely black. They radiate energy, and over time, this causes them to shrink and eventually vanish. But more recent work challenges that conclusion. Modern theoretical physics proposes that black holes might not erase information after all. There are now three competing pictures of what happens inside a black hole. One particularly imaginative idea is that the interior of black holes might be like a network of quantum wormholes, structures predicted in some solutions of general relativity that connect distant regions of space and time. This idea leads to a unifying concept. Space and time themselves might not be fundamental. Instead, they could emerge from a more basic quantum description of reality. In this view, space-time is an emergent phenomenon, much like consciousness emerges from neurons, or temperature emerges from molecular motion. Space and time are not fundamental. They emerge from something else, something deeper. The professor likens this to emergent phenomena in other areas of science. For instance, life emerges from non-living molecules given the right conditions. Similarly, space-time might emerge from a vast quantum computational network encoding all physical reality. Hawking's calculations revealed that black holes also possess entropy, a measure of disorder or information content, and temperature. In fact, the entropy of a black hole is proportional to the area of its event horizon, not its volume. This is a revolutionary insight because it implies that information about the interior of a black hole is encoded on its boundary. This idea gave birth to the holographic principle, a cornerstone of modern theoretical physics. Imagine space itself as being pixelated. Each pixel encodes one bit of information, and the total number of bits corresponds to the surface area of the event horizon in Planck units. This perspective suggests a radically new view of the universe, one in which the entire reality we perceive as three-dimensional may actually be a projection of information encoded on a two-dimensional surface. To summarize, in this section, Cox brings together gravity, quantum mechanics, information theory, and the deep philosophical questions about the nature of reality. The study of black holes is not just about understanding exotic cosmic objects. It is about unlocking the very fabric of reality. We are beginning to get a glimpse of how information might be encoded in the building blocks of space-time, and it looks surprisingly like how we store information in quantum computers. Thus, rather than seeing black holes as dead ends in space, we now view them as windows into the most fundamental aspects of the universe. They force us to confront deep questions about what space and time are, how information behaves in the universe, and whether reality itself is emergent from something even more profound. This is the mystery and wonder of modern cosmology. As Professor Brian Cox leads us further along the trail of cosmic inquiry, he ventures into the realms of astrobiology, planetary science, and existential reflection. He begins by turning our attention from the cosmological canvas to more tangible questions about life, not just on Earth, but elsewhere in the solar system and beyond. We do know, he remarks, that life on Earth emerged relatively quickly once conditions stabilized. The origin of life must therefore be a transition from geochemistry to biochemistry. Professor Cox then explains that within a few 100 million years of Earth's formation, signs of biological activity appear in the fossil record. This suggests that the origin of life might not require a miracle. It might simply need the right conditions. Cox points to alkaline hydrothermal vents, specifically located deep within Earth's oceans, as a likely environment where life may have originated. These environments are rich in minerals, chemistry, and energy gradients, all essential ingredients for biochemical complexity. Given the right geochemical gradients, patterns can emerge that copy themselves. And when you have that, you have the basis for evolution by natural selection. He then connects this theory to modern exploration, explaining why NASA and ESA are targeting similar environments elsewhere in the solar system. Mars, for instance, had standing water billions of years ago. The Curiosity and Perseverance rovers have uncovered compelling geological evidence, including oxidized iron patches only known to form in the presence of both water and biology on Earth. Beyond Mars, Cox describes missions heading to the icy moons of Jupiter and Saturn, Europa and Enceladus. These moons, though frozen on the surface, hide global subsurface oceans beneath their icy shells. The surface of Enceladus, for instance, is venting water and organic molecules into space. We don't even have to land to sample it, just fly through the plumes. And yet, despite all this potential, a profound caveat looms. Life on Earth remained unicellular for almost 4 billion years. Complex life, multicellular organisms, and eventually civilizations only emerged in the last 500 million years. If it takes 4 billion years of stable conditions to evolve intelligence and civilization, then despite the potential for billions of habitable worlds, intelligent life may still be rare. Knowing what I know about evolution and biology, I look at all those stars and planets, and I suspect most of them are just slime. If we destroy this civilization through inaction, then we may be responsible for silencing the only meaningful voice in our galaxy. The message from astronomy, cosmology, and biology is that this world, our Earth, is possibly the only place in the known universe where meaning exists. Meaning, like consciousness, emerges from complexity. It is not an illusion, it is real, but fragile. In closing, Cox references the image of the Earth and Moon taken together as crescent slivers against the backdrop of space. It is a visual echo of Carl Sagan's pale blue dot, a symbol of how precious and rare our home truly is. It may be that despite the scale of the universe, this world is the only one where meaning exists. That makes it not insignificant, but unique. That makes it beautiful. And that makes our responsibility to protect it absolute. Professor Cox concludes his profound lecture with a deeply reflective message, one that transcends science and touches on responsibility, meaning, and the uniqueness of life. At the end of the talk I gave to the world leaders at COP26 in Glasgow, I had only 1 minute. I could have spoken about carbon emissions and targets, but instead I said this: complex life may be extremely rare in the universe, and if we destroy it here through inaction or ignorance, then we may be responsible for extinguishing the only flicker of meaning in an otherwise indifferent galaxy. He emphasizes that Earth may be the only place in the universe where life, and more importantly, conscious life, has emerged. Life that can ask questions, explore the stars, and dream of the future. This world is fragile. It might be the only island in a vast cosmic ocean where atoms have come together to think, to feel, to wonder. The universe has no intrinsic meaning unless there are beings capable of perceiving and assigning meaning to it. Meaning, therefore, is emergent. It arises from complexity, from life, and from consciousness. Just as time and space may emerge from some deeper quantum substrate, meaning may emerge from life. And if that's true, then Earth is not just an astronomical object orbiting a star. It is a crucible of meaning, a sanctuary where the universe itself becomes aware of its own existence. We are not merely observers, we are participants in the unfolding story of the cosmos. If we are to be stewards of knowledge, of civilization, of possibility itself, we must protect this fragile world, because without us, the universe may go back to silence. The lecture ends with one of Professor Cox's favorite images, a stunning photograph of Earth and the Moon seen together from space. Just two thin crescents adrift in the black void, a reminder of both our vulnerability and our significance. The laws of nature allowed this place to form. They allowed atoms to become conscious. That alone is an extraordinary fact. But now it is up to us, through science, wisdom, and responsibility, to ensure that meaning endures. From the depths of galaxies, black holes, and event horizons to the philosophical frontiers of creation and meaning, this video has taken us on a journey through the profound insights of Professor Brian Cox. But this wasn't merely a scientific exposition. It was an invitation to rethink ourselves, our future, and the unique role consciousness plays in the vast theater of the cosmos. If, among trillions of planets scattered across countless galaxies, only we have reached the level of thought, science, and wonder, then the greatest responsibility in the universe may rest on our shoulders, the preservation of awareness. Here at Fact Up, this video was crafted not just to inform, but to awaken, to stir the shared human impulse to seek truth, question existence, and confront the unknown. If there are any imperfections or inaccuracies in how this content was presented, they are mine, not the professor's. I attended his April 2025 lecture in San Diego and have done my best to convey his ideas faithfully and meaningfully. Now it's your turn. Share this video, comment with your thoughts, and subscribe to Fact Up to join us as we explore the mysteries of the universe, one truth at a time. Fact Up is where science, philosophy, and curiosity converge, and you are an essential part of the journey. Until the next video, stay curious.